So last time we constructed representations of supersymmetry algebra in terms of one particle massive states. Today we'll construct massless representations. Now we start with the statement that a massless particle can always be cast into a light cone frame of the kind that its momentum p nu E in the 0 direction and 3 momentum align it along the z direction. So that p mu is p square minus 3 momentum square is 0. Now we already discussed that a massless particle is described by prescribing its energy E and its helicity lambda. And helicity lambda is the 0th component of the Pauli-Lubansky vector divided by length of the 3 momentum, and which is same as J dot P 3 momentum divided by mod P. And J is the rotation generator. And for this P mu, where 3 momentum is in the z direction, this is simply the value of Jz for that state. I think last time we did this exercise of JL commutator with the supercharge K alpha I is with a minus sign, right? Minus half sigma L alpha beta Q beta I. And JL with Q bar alpha I. Did we write it somewhere? Is with the plus sign. Q bar beta dot I sigma L beta dot alpha dot. So now if I contract this with 3 momenta, And 3 momenta that we have here has only z component. So it simply is minus half sigma z alpha beta and beta I. And this object is W0. So I can write W0 Q alpha I is, sorry, there is an E here, right? Because PZ component is E. So you take E here, that gives me is minus half E sigma z alpha beta to beta I. So if I were to now evaluate this commutator on a state W0 Q alpha I acting on a state E lambda, given energy, given helicity, this object commutator is this W is Q alpha acting on W0 on state E lambda minus E by 2 sigma z alpha beta Q beta I. Yes. Did I do it right? And this object is lambda acting on this. So you replace it by lambda, and let me write this as now. This is lambda times E. Lambda times E. So take E out. And this is lambda minus 1/2 sigma z alpha beta Q beta I. Lambda times a unit matrix, sigma z. And take this W on this, this E on this side. So now if I write it explicitly on components, Q1 I E lambda and Q2 I E lambda sigma z is 1 0 0 minus 1. So I pick lambda here. So sorry. So what do I pick up here? I pick lambda minus 1/2 Q beta I on E lambda, and lambda, did I have it right? Upper one is minus and lower one is plus, yes. Now this is the helicity operator. This tells me that the helicity of this state is lambda minus 1/2. And helicity of Q2 acting on E lambda, this state, is lambda minus lambda plus 1/2. So what it tells me is that Q1 operating on a state decreases helicity by 1/2 unit, and Q2 acting on a state reduces it, increases the helicity by half. Q alpha Q1I in lowers helicity by half unit. Q2I raises helicity by half unit. Exercise. Now use this second relation, do the same exercise again, and argue that Q bar 1 dot I and Q bar 2 dot I raise and lower helicity by a half unit respectively. Not surprising, the only difference is sign, that's what it'll interchange. So Q1 was lowering, Q1 dot will raise. Q2 was raising by half unit, Q2 dot will lower. So that's what one property. Second property is, let's write now the supersymmetric algebra for particles whose momentum is of this kind. For momentum is in this frame. So supersymmetric algebra. So SUSY algebra in light cone frame. Now we have Q alpha I, Q beta j, commutator 0. We have no central charges. Q bar alpha dot I, Q bar beta dot j, anticommutator 0, and Q alpha I, Q bar alpha dot j. This object we had was twice delta ij sigma mu p mu alpha alpha dot.
What was the argument behind mention of the central charge?
With that we assume. There is no argument for this. We are constructing representations of algebras without central charge now. And with central charges we will discuss later. Now for this light cone frame, sigma dot mu is sigma 0 p0 plus sigma z pz alpha alpha dot, and that is 2e sigma 0 plus sigma z, this delta ij here, alpha alpha dot. Because only P0 component is 0 and and Pz component is non-zero, and both of them are E. This is what it is. Now sigma 0 is a unit matrix. Sigma z is what it is. Therefore, this object is first one is 0, right? The only non-zero component is the first one. This is 1 minus 1, 0. So now this object, let me rewrite explicitly in terms of components. Let me write the two one. That is corresponding to this, that is 0. And then is that clear? So now look at these objects. Q2 bar is 0. Q2 is 0. Q2 bar is 0. So the algebra of supercharges with label 2's is all 0. That means the algebra is trivial. There's nothing in that. So you can take all Q2's to be 0. So this leaves only the algebras of Q1s. So Q1 I Q bar 1 dot j and Q1 I Q1 j 0 Q1 dot I Q1 dot j bar. So we have only this algebra. I think I got some number wrong, right? 2 should be 4, huh? Because there is 2 here, there's 2 is here, 4. Is that clear? So the Q2 charges are all 0 because all the algebras, anti-commuters amongst Q's are 0. So I can take states on which Q2's are identically 0. So which means Q2's are no symmetries. So we have reduced symmetry in this light cone frame. Instead of 2n charges, n capital, from I going to 1 to n, and alpha taking 1 or 2 values, from 2n charges and their conjugates, it has reduced to only n charges and their conjugates. N is 1, 2, 3 because of up to capital N because of i's. Now let me make a convenient redefinition. Call it AI is Q1I divided by 4E. This convenient normalization. And AI dagger I call is Q1 dot I bar 4E. There's just a convenient redefinition. And write the algebra on A's. AI anti-commutator AJ is 0. AI dagger AJ dagger anti-commutator is 0. And AI AJ dagger anti-commutator is delta IJ. I is 1 to n. N fermionic oscillators. So what we have in algebra of n fermionic oscillators, and we have learned the tricks of how to construct their representations. So we'll construct their representations. How do we do that? Start with a vacuum. Vacuum state, where word vacuum has very contextual special meaning here. It's not the physical vacuum of the theory, it's the vacuum of this algebra. Defined by the destruction operators on that. And since we said massless states are described by prescribing the energy value and helicity, so AI is acting on E, the state E, a lambda or 0. So we start with such a state and apply creation operators on it and create the representation of this algebra. Creation operators are A daggers. Apply AI daggers on this to generate a representation. So 1 AI, 2 AI daggers, 3 AI daggers, 4 AI daggers, all possible AI daggers on this. And since now A's are, A dagger is Q1 dot bar, Q bar 1 dot. And what does Q1 bar do? We just set up this property of it. It raises the helicity by half unit. So AI daggers increase helicity by a half unit. That is, if I apply AI dagger on this state E lambda, I'll get a new state with the same E, but lambda increased by half unit. Now let me just make a table of a representation. Construct this representation in a tabular form, a general representation. So I start with this. Label the states, label number of states of that kind, number of states, and helicity value. And whether they are bosonic or fermionic, I'll list them separately. So start with the ground state, which is E lambda. It is one state, and I'll write it in this funny notation. That's one. And it has helicity lambda. It could be a boson or a fermion, depending upon whether lambda is half integer or integer. If it's a half integer, it's a fermion. If it is an integer or 0, then it's a boson. And apply now AI dagger on this. Since there are n AIs, I goes from 1, 2, 3, 4 up to n, I can create n such states. And this n, I'll write it and the helicity would be increased by half unit. So if the starting one was a boson, it will become a fermion, and the starting one was a fermion, it will become a boson. Now let me apply two of them. Two A daggers. Some normalization. Now recall, because these are fermionic oscillators, they anticommute amongst themselves, daggers. So if I take a particular value of I1 here, I cannot take the same value of here, because that would be square of that operator, and that is 0. So which means I1 should be not same as I2. Now, how many of them are there? Such states. Now, I1 and I2 take these values, n values. It essentially makes an n cross n antisymmetric matrix. So, number of components of an n cross n antisymmetric matrix is n into n minus 1 by 2. And this would be helicity plus 1. And if this was fermion, this will become boson. If this was boson, this will become fermion. And go on, then 3 of them, 4 of them, and finally n of them. Can anybody tell me how many states these are? It's 1. And what is the helicity? There are n steps in this. 0, 1, 2, this is n plus 1. So these are n steps. This is first. After that, there are n steps here. So n by 2. Now, is this a boson or a fermion? That will depend on what lambda is. That will depend also whether n is even or odd. So if this was a boson, that means this is integer, then for n even, it's a boson if starting was boson, and it's a fermion if starting was fermion. For n odd, if starting was boson, it would be a fermion, and in starting was fermion, this would be a boson. Do I have right? Yes. So that gives us a representation. And again here, for the same reason, no labels are repeated. So I1 is not same as I2, is not same as In. So how many total states in this supermultiplet? Just to remind you, so how many total representations? total number of states in this representation. And like we already said it last time, this is a funny way of writing 1 plus 1. Can anybody recall what was the number of states for the massive multiplet? 2n, 2 to the 2n. Now this is 2 to the n. So, contrast with the dimension of massive supermultiplet 2 to the 2n. Now let me take some specific values for lambdas, just to explicitly write down some simple examples. Consider n equal to 1, a simple case. N equal to 1, there is only one A oscillator and one A dagger oscillator. So, if we have a starting state, vacuum state E lambda, then I can create a state E by acting one A dagger on it, and that would be that makes a n equal to 1 supermultiplet. With a starting helicity lambda, one component helicity lambda. But in physics nature, we know we have a CPT invariance. This is not a CPT self-conjugate multiplet, because if it was CPT self-conjugate multiplet, it should have also had lambda helicity and minus lambda helicity, because they are each other's CPT conjugates, particle and antiparticle. And lambda plus half, it should have also had minus lambda plus half. So, we for CPT invariance add states with helicity minus lambda and minus but to do that, whatever I add, that should also be a representation of the algebra, right? And that, how do I construct that? I'll construct that as by taking ground state to be this. This one. And apply A dagger on that. That's another representation. So these together will make an CPT respecting n equal to 1 supermultiplet. Clear? So together CPT respecting supermultiplet. As a representation of the SUSY algebra, it's a reducible representation. It's made of two of them. Yes. Starting state is minus lambda plus half. Minus, and A dagger increases it by half unit. Now, what I want is that I constructed a multiplet which is made of helicity lambda and lambda plus half. And CPT invariant theory would have, these are particles, they are antiparticles. Antiparticles will have helicity minus of that, right? Huh? So I need particles with helicity minus lambda, which would be an antiparticle of this, and minus this, which would be an antiparticle of this. But these themselves must make a supermultiplet. How do I construct that? This is the way to construct it. So they make a CPT respecting supermultiplet of n equal to 1. Now let's specialize further. Now take lambda to be 0, just an example, which means start with E 0. This is still n equal to 1. And apply A dagger on that. And take second multiplet, ground state, with helicity minus half. Apply A dagger on it. This is a CPT self-conjugate multiplet, because this object is CPT conjugate of this, and scalar, these are two scalars. I put the same, I did not put a prime on this, but this is a different state from this, because this is this. So you could have said earlier, I had put a prime on such things. They are different states. These together give us a representation, give us a scalar, and gives two scalars. In fact, it's a scalar and a pseudoscalar. And two fermionic states. This is massless scalar supermultiplet. Maybe going back here, it's an obvious statement, but let me make it again. By now we are familiar with. These two n states, half of them are bosonic, half of them are fermionic. Right? But half bosonic, half fermionic. Now here we are seeing them explicitly again. 2 bosonic states, 2 fermionic states in this one multiplet, which is made up of 2 supersymmetric multiplets. Now let me take next one. Starting one, I take E and half. The vacuum state is helicity half, fermionic vacuum state, and apply a dagger on it. So let me call this A and B, A and B. So this is a fermion, helicity half. This is a boson, helicity 1. Again, I have to add CPT conjugate states there. So I start with E minus 1, apply E dagger minus 1 to it. Now this is CP conjugate of that, this is CP conjugate of that. I have 2 fermionic states, 2 bosonic states. So 2 bosons, 2 fermions. All massless. This is photon supermultiplet. Two helicity states associated with 2 helicity states of a photon, 2 polarization of light, and their super partners, a Majorana fermion, chargeless Majorana fermion with 2 helicity states, massless. So this has a photon and a massless Majorana fermion. Photon has 2 states, a Majorana fermion has 2 states. Perfect. Let's take a third example. Is this no? Start with 3 halves. They have to be. I don't see that here, because if they have to be partners of photon, they have to be chargeless, because supersymmetry doesn't change the charge. All right. See, if I identify this as a photon state, it is chargeless. So I generate a state from there that must also be chargeless. That's why it must be Majorana. Majorana fermions are chargeless fermions. All right, so I start with the ground state with helicity 3 halves and operate a dagger on that. I get helicity 2. And to get the CPD conjugates, I start with a state with helicity minus 2. I apply a dagger to it. This together makes a CPD conjugate multiplet, CPD self-conjugate multiplet, made up of 2 particles of helicity 2 and minus 2, and 2 particles of helicity through fermionic particles of helicity 3 and minus 3. This is graviton supermultiplet. Graviton is spin 2 object. It has 2 states, helicity 2 and helicity 2 minus 2, and its superpartner is a gravitino. Give it a name, gravitino, with 2 helicity states, with helicity values plus 3/2 and minus 3/2. So it's a graviton plus gravitino spin or helicity plus minus 3/2. Massless gravitino. This was n equal to 1. Now I can do the same exercise for n equal to 2, n equal to 4, a little more complicated, and figure it out what are the various representations. I mean, most general one is tabulated there. Takes some special examples to understand what they look like. In particular, let me give you 2 exercises. Starting with vacuum state omega to be E minus 1, helicity minus 1. Construct a n equal to 4 supermultiplet. So take 4 oscillators, A1, A2, A3, A4, and they are daggers. Take the vacuum to be annihilated by all undaggered ones. Act daggered ones, 4 of them, hit the sequence that we tabulated there, and figure out how many, what are the helicities of the different states that are so created, what is their number. And convince yourself that this is a CPT self-conjugate multiplet. You don't need to add anything to it. On its own, it's a CPT self-conjugate multiplet. And this representation is particularly very interesting because this is the representation that you set up in building n equal to 4 Young-Mills theory. This is a n equal 4 Young-Mills supermultiplet. Well, Young-Mills theory is a non-abelian theory. So for every generator of the non-abelian group, you have one multiplet of this kind. That's an internal symmetry. For every generator of the internal symmetry, SUN, Young-Mills, you will have one such multiplet. And it will have highest spin 1, helicity 1 or plus 1. We started with the highest helicity value is +1 and the lowest one is -1. So which means it will have helicity 0, ±½ ±1 states of certain number. That number you figure it out. Second example. Start with vacuum state with helicity -2. And construct n equal to 8 supermultiplet. And you will discover that this is also a self-conjugate multiplet. And it's a multiplet of n equal to 8 supergravity. It has graviton because there are helicity -2 states, and the highest helicity state that you will find is +2. So it has a graviton and other content. So it is the n equal to 4 supergravity multiplet, n equal to 8 supergravity multiplet. Now, from these examples, you would have already noticed that if I take n larger than 4, then whatever spin I start with, I will end up with some helicity state here which is larger than 1, +1, or smaller than -1. So which means spin larger than 1. If n is larger than 4, 5, 6, 8, for example, you already have spin 2. Is that clear? Convince yourself that's true. Because simply number of oscillators are 5, they will increase each one of each one of them will increase the helicity by ½ unit. You just see the spread. Spread is going to be take you at least some state will be of spin larger than 1. But we know, and these are all massless, right? We are talking massless states. No renormalizable field theories with spin greater than 1 So that tells you that if you want a renormalizable field theory description of the supermultiplets, that n cannot be larger than 4. So no renormalizable field theories with spin greater than 1. Therefore, for renormalizable field theories, n is always less than 4 or equal to 4. Any? Sorry, I did put the ulta. Right? It should be less than 4. Yes. Now, what was the question?
For n is equal to 1 also, we got spin 2.
We got spin 2, but so spin, that is not renormalizable, but we also got spin 1 and 1. So some supermultiplets, even for n equal to 1, will be non-renormalizable. But for n equal to 5 and more, there will be no supermultiplet that you can construct which will give you, for which you can set up a renormalizable field theory. Okay? So that is the maximal number of supersymmetries in which renormalizable field theories can be written. Right? Now, sometimes we don't worry about renormalizability. Partly the reason is we know that there is a force in nature, gravitational force, and we don't have a renormalizable description of gravitational force. So we don't understand that. So we also need to do business with theories which are not renormalizable. So if we give up on renormalization, then ask the question, how far can we go in n, capital N? But there's one more problem. See, we give up renormalizability. Can I write a non-renormalizable field theories for any higher spins? Spin 3/2, spin 2, gravity, we know, we can't do it. Spin 5/2, spin 3. Now the answer is that even classical theory is not, you cannot write a classical field theory for spins with fields with spins 5/2 and above. Even classical field theory, self-consistent classical field theories, even consistent classical field theories with spin 5/2 and above are not possible. In fact, even spin 3/2 classical field theory is self-consistent. Gravitino theory. If I want to write down a spin 3/2 interacting theory, generically it's inconsistent, except in the situation when it comes along with a graviton as a multiplet of supersymmetry. So supergravity theory containing spin 3/2 is classically a consistent field theory, but spin 3/2 on its own is not. So that's another reason why supergravity is interesting. Consistent means the constraint structure of the gauge structure doesn't have a consistent, self-consistent solutions. Yes, these are theorems. These are theorems. I'm not proving them. These are theorems. But we'll apply these theorems to see what it means for us. In fact, for a long time it was believed that it's in fact a result by somebody who we know here, George Sudarshan, and one of his collaborators called Johnson, Sudarshan-Johnson theorem. They said they analyzed the constraint system of hard spin theories. No hard spin theories are possible beyond spin 1. So even spin 3/2 was excluded. And then now when the supergravity came in, people found out that all those problems with spin 3/2 disappear if there is a graviton hanging with them. So supergravity constraint equations do have a self-consistent solutions. So now, which means that highest spin that we can allow in our theory is spin 2. Now, convince yourself, if I take n to be larger than 8, I will at least produce some states with spin 5/2, greater than spin 2. I'll produce. We are talking 4 dimensions. This is all 4 dimensions. So convince yourself that just simply take this number of steps you need it. If it's n is 9 or n is 10, you will need 5 steps. So finally, even if you started with 0, you will end up with 5/2. Or if you started with minus 5/2, you will end up, you started with minus half as a starting state, somewhere you will go and create. So n equal to 8 then is the highest number in which you can write a classical quantum field theory. So maximal value of n for a gravity theory is n. So n equal to 8 is the maximal supergravity theory. Any other theory with n greater than 8 will have spin 5 halves. Okay. I still have half an hour. So now let me start a discussion on representations of SUSY algebras with central charges. We had ignored central charges, we assumed them all to be 0. They have very nice properties, and that's why we are discussing them separately. SUSY with central charges. So let me recall the algebra. Q alpha I, Q beta j, anticommutator is twice root 2 epsilon alpha beta Zij. And Q bar alpha I dot Q bar beta dot j, anticommutator is 2 square root 2 epsilon alpha dot beta dot Z bar Ij. Now Z bar Ij is nothing but Zij that we have here, an adjoint of this. An adjoint is Z star and Ji, interchange Ji's. That is minus Zij star, because Zi's are, Ij's are antisymmetric matrices. They are antisymmetric in labels I and J. And then we have Q alpha I, Q bar alpha dot J, anticommutator 2 sigma mu P mu alpha dot alpha and delta Ij. This is what we have. Clearly, for n equal to 1, there is no central charge. Because Z is an antisymmetric object with labels I and J. So we have talked about n greater than 2, 2 or greater than greater have central charges. So let me take n equal to 2 in particular. What happens to the algebra? Anticommutator of Q alpha I, Q beta j is 2 root 2 epsilon alpha beta. Zij is a simply a 2 cross 2 anti-matrix, antisymmetric matrix. So that I can write as epsilon Ij times Z. I is 1, 2, j is 1, 2, and epsilon Ij is antisymmetric in I and j index with values +1 or -1 or 0. And same I hope these dots are not clear on the blackboard, they get lost. Alpha dot beta dot ij bar is 2 root 2 epsilon alpha dot beta dot epsilon ij z. Z is some complex number. And then q alpha I, q the bar alpha dot j I j take values 1 and 2. So n equal to 2 theory has only one central charge, and that's what we have called Z, a complex central charge. But Z need not be complex, because the phase of this Z I can take it on this side. Sorry, this is Z bar, right? This is complex conjugate of this. Take it on this side and absorb the redefinition of Q's. Half of it here, half of it here. Take the phase of Z bar, which is opposite of that. That I absorb half of it here, half of it here. And so phase of Z can be rotated away by a U1 or transformation on supercharges. So it's only mod Z that is the central charge. So we have only one real central charge in this theory. So only one central charge, that is mod Z. Now let's do a sum, reorganize this algebra in a particular way by constructing two set of operators, call it A alpha, 1 by square root 2, Q alpha 1. This is the I symbol. I takes value 1 and 2, 1. Alpha is the spinor value, plus epsilon alpha beta q beta q bar beta 2. 2 is. Now I have introduced symbols epsilon alpha beta bar and they are defined as with values 1, 1 dot equal to 0, same as 1, 2, 2 dot, and 1, 2 dot as minus 1, 2, 1 dot, and that equal to be minus 1. Is that clear? This is earlier we did not define epsilons with mixed indices alpha and alpha dot. Now we have defined them with mixed indices. But then we're giving them specific values, what it means. It's antisymmetric in the interchange of these two. That means this 1, 2 is minus 2 dot 1, and that's minus 1. So you construct this, a linear combination of q's, and construct orthogonal combination call it B alpha. And A alpha dagger conjugate of this. It's just reorganizing the set of charges I had here in terms of these new ones. But if I do it that, then it has some nice properties. And that we leave it as an exercise. It's only just substitute that algebra into this to figure out what is the algebra of A's and B's. Exercise. A alpha, A beta dagger anti-commutator is twice m plus root 2 z delta alpha beta. Now, one more thing. So, we dealing with massive representations. So, we will take P mu to be m 0 0 0. So, use this fact and you will see that this is what it is. And B alpha, B beta dagger this is mod z, right? Is it clear? You want me to leave them earlier, right? So, for massive particles, you take P mu to be like that, and all other anti-commutators 0, which means A with A, B with B, A dagger with A dagger, B dagger with B dagger, and A with B dagger. Now, there is one property that this algebra already shows us. This shows us that this algebra implies that m is always greater than root 2 mod z. Okay. Is it? No. Yes. So that this is positive. Why? Because if I take a state omega, and calculate omega, a vacuum state, because for a vacuum state omega, that means A alpha on omega is 0, B alpha on omega is 0. In particular, let me calculate expectation value of B alpha, B alpha dagger plus B alpha dagger, B alpha omega. Same alpha, 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 but not summed. For a given value of alpha, 1, 1, 1, 1, or any other equation you want to write it, 2, 2, and 2, 2. That's separate equation. For a given value of alpha, for a given value of alpha. That means it's a repeating index, but it's not summed. Now let me evaluate this. Because B alpha on omega is 0. So that gives me omega B alpha dagger on omega. Is that clear? And that gives me, this is norm square of the state, B alpha dagger on omega. Therefore, this is positive, or at best 0, at worst it's 0. But what is on the left hand side? This object. Use the algebra. Take the same value, 1, 1, that's 1. This is this. That tells me this object has to be positive. That tells me m has to be greater than or equal to root 2p. And m equal to, when this equality holds, is a very special value. M equal to root 2 mod z is a special value. And that we'll discuss separately. But for m not equal to 2 mod z, we could set up now a representation for this algebra. And the representation for this algebra, and it goes exactly the way that we had set up for massive particles without central charge. All I have to do is that reorganize them, absorb this in the normalization of this, or normalization of this. I have two sets of harmonic oscillators, and do the exercise, repeat the exercise the way we did it earlier. So there is no difference with the representation of massive supermultiplets that we did earlier with central charge, these theories with central charges. When m is not root 2 z. But when m is root 2 z, the representation changes. And that we'll do the next time. And but when or states with m equal to root 2 mod z are called, so let me first write it, same representation theory as of massive multiple without central charges. This is different, and this is called Bogolo. How do you write it? These guys have funny names. Bogomoloni states. And we'll discuss Bogomoloni states next time.